All right, in previous videos, we looked at the idea of kinematic equations to describe the motions of objects undergoing things like acceleration with particular velocities and things like that. The stipulation for using the kinematic equations was that the acceleration of the object must be constant. And what I said was that this represents a subset of all possible physical systems, but it turns out to be a pretty interesting subset. There are all sorts of physical systems in which the acceleration is not constant, but there is one situation in which we all find ourselves every day for which the acceleration is constant, and that is the acceleration of an object under the influence of gravity. So the common wisdom for a couple thousand years was that heavier objects accelerated at a greater rate than light objects. There are lots of good reasons people made that assumption. The common way that it's dismissed is that, oh, well, ancient people didn't perform experiments. But that's kind of ridiculous. They did. There are some issues associated with that as well. But if you think about it, if you drop a rock, it's obvious that it accelerates pretty quickly. But if you drop a flat piece of paper or a feather, it doesn't, right? It kind of flutters to the ground. Now we understand that that involves air resistance, but in the ancient times that wasn't really well understood. And so people assumed that heavier objects fell faster or accelerated at a greater rate than lighter objects. The person who is credited with discounting that notion is Galileo. The story, which is probably apocryphal, says that Galileo went up to the top of the Leaning Tower of Pisa and dropped off two objects, a heavy object and a light object, and then noticed that they hit the ground at the same time. And that actually does happen. This story is fun to think about, but it's probably apocryphal, probably didn't happen. What we know that Galileo did do, though, was roll different sized discs down an inclined plane or inclined planes and noticed that they reached the bottom at equivalent times. So Galileo, at any rate, is credited with figuring out that everything that's falling accelerates at the same rate. Now, we've got to make some assumptions there. We are going to assume that that's true, we are going to ignore air resistance. We will handle air resistance at some point, but we're going to assume that if we drop something, the air resistance is at best negligible, and we're going to summarily ignore it. If that's true, if the only thing acting on an object is gravity, and I'll write this down. If an object is only subject to gravity, nothing else acting on it like air resistance or rocket boosters or anything else, if it's only subject to gravity, its acceleration is equal to, I'm going to write down this number, 9.81 meters per second squared. Now, some of you will use 9.8 in previous classes. Some of you might have seen, people use 10 sometimes. 9.81 is actually, turns out to be an average value. It turns out that the acceleration due to gravity varies as you move over the surface of the Earth, depending on lots of different things that we'll talk about when we actually get to talking about the force of gravity. But right now we're talking about the acceleration due to gravity, and this is a good enough number for our purposes. This is kind of like 98.6 degrees Fahrenheit, right? That's an average value. This is an average value, but we're going to go with it. So in this class, we'll use 9.81. I don't mind if you use 9.8, but on an exam where I have particular numbers set up to be right in Canvas, be as specific as you can. Let's use 9.81 meters per second squared. So if an object is only subject to gravity, its acceleration turns out to be 9.81 meters per second squared. Downwards, how do I know downwards? Well, gravity always acts downwards, right? So the acceleration due to gravity is normally denoted G. G is, it's improper to say gravity when you're talking about little g. Gravity is a force, and we haven't talked about forces yet. We're talking about accelerations. This is the acceleration due to gravity. I'm going to be persnickety about the language. This is not gravity. This is the acceleration due to gravity. We define it as that same number, 9.81 meters per second squared. We define it positively. Please notice that this is not minus 9.81. G is defined as positive 9.81 meters per second squared. We define it positively for the simple fact that the coordinate system is yours to control, right? So if you decide that up is the positive direction, we've already said that gravity acts downward, so this is always pointed downward. This is negative G. The negative is your choice to put out front if your coordinate system is upwardly positive. If you decide that down is the positive direction, G is still down, but this time we call it positive. So whether or not you put a negative sign in front of the G or not, G itself is always positively defined. The negative sign comes from your choice of coordinate system. Now, once you have this, and remember the stipulations we have to make. No air resistance, basically, is the one that we're gonna focus on. Once you have that, well, this is a constant. And so you can reform all of your kinematic equations with this in place of the acceleration. For instance, let's just pick out one. V final is equal to V initial plus AT. Let's assume, for the sake of argument, that you say that you say that up is positive, which means that down would be negative, and you find that something is accelerating due to the influence of gravity. You can now rewrite this equation, V final is equal to V initial, and you're going to substitute in minus G for A minus GT. No big deal. You start with this equation, and then you plug in what you need to for G or negative G as your coordinate system has it. All right, so that's the acceleration due to gravity. We give a special name to objects undergoing this acceleration. That name is free fall. By definition, free fall means something is accelerating at little g. I'm saying little g because later we're going to see a big G, and we've got to be a little bit clear. But free fall is a particular state of motion in which something is only subject to gravity and is therefore accelerating at 9.81 meters per second squared, or G, downwards. That's free fall.